Today, we want to start looking at the next big thing, which is finding antiderivatives. As the name implies, antiderivatives is just going to be differentiation in reverse. These are the antiderivatives that show up in that fundamental theorem of calculus. So all that stuff we learned about differentiation, we now have to learn it backwards. The fun thing about integration or antiderivatives is that although differentiation is a nice, easy process where we have product rule, quotient rule, and chain rule, and that's got us covered for anything that we want to differentiate, integration is not that way at all. There are some functions that do not have nice antiderivatives. And so it's much more important, it's important when we're integrating things that we categorize what kind of process we're going to use. It's very similar to deciding whether we're going to use product rule, quotient rule, chain rule, although it's less obvious because it's not as easy as identifying when we're multiplying, when we're dividing, or when we're doing a composition of functions. So let's start with the beginning. Let's start with the basics. All your derivative rules are now integral rules. All your derivatives are now integrals as well. I don't need to shout this so much. All your derivatives are now integrals as well. When you learn things in math, you have to learn them forwards and backwards. Now we're going to be doing things backwards. So what I mean is that we know that the derivative with respect to x of, let's say, x squared minus 5x plus 3 is equal to 2x minus 5. This also contains integral information. If we integrate the function 2x minus 5, we'll get back to where we started, minus a little bit of information that always gets lost. So if we look at an integral of 2x minus 5 dx, we'll get back to where we started. The integral of 2x is x squared. The integral of minus 5 is minus 5x. And then we're missing some information. The way we deal with this is to put at the end, when we do an indefinite integral like this, or find an antiderivative, we put some constant at the end. And this is an arbitrary constant. This is lost information. When you take the derivative of a constant is 0, we lose that information. So it's not strictly an invertible process, because derivative of every constant is equal to 0. But it's invertible enough because we know it's just a constant that got missing. There's not some extra part of the function. This is just going to shift it up and down. And we call this the constant of integration. Any questions?
So we basically just assume that there's always a constant, even though there may not have been.
There may not have been. The constant might have been 0, but we don't know what it was. We need more information to figure out what the constant is. We would need to know something about the function to figure out what this constant is. We need more info. To find this constant. We would need more information to determine the plus c. Here are some other things that I did with this statement. I wrote the integral of 2x minus 5 dx, but this is not a definite integral because it doesn't have an interval from a to b. So this is an integral that's called an indefinite integral. Indefinite integral. What makes it indefinite is that there's no interval from a to b. So we're not integrating it over some interval from a to b. So that makes a definite integral. This one is an indefinite integral because there's no interval over which we are integrating. So this is a symbol that says do an indefinite integral or find an antiderivative. Just like writing d over dx in front of a function means take the derivative of the function with respect to x, writing this around a function, integral dx, says integrate this function with respect to x, or find an antiderivative of the function with respect to x. So let's look at some more examples. Any questions? So every statement that we had about derivatives, we need to re-examine them and rewrite them as integral statements. So we need to write all our derivatives as integrals. We need to write all our derivatives as indefinite integrals. So where before we said the derivative with respect to x of x to the n is nx to the n minus 1, we multiply by the exponent, then subtract 1 from the exponent. We need to rearrange this to say that the integral of x to the n dx. So we just invert this process. We add 1 to the exponent, then divide by the exponent. And say there was some information that we might have lost, so we put a plus c for a constant of integration. We know that the derivative with respect to x of sine x is cosine x. So the integral of cosine x dx is sine x plus some constant. We know that the derivative of cosine x is minus sine x. So the integral of sine x dx is minus cosine x plus some constant. Any questions? We have to do all of them, everything that we know about derivatives.
Is it negative cosine or is it cosine?
Negative cosine, because the derivative of cosine is negative sine, so the integral of regular sine is negative cosine. The integral of negative sine is positive cosine, so we move the negative back and forth. The derivative of tangent is secant squared. So the integral of secant squared is tangent. everything that we know about derivatives is now something we know about integrals. Any questions? The derivative of e to the x is e to the x. So the integral of e to the x dx is e to the x plus some constant. Any questions? Just like when we were doing derivatives, we tried to write, if we can, we write powers of x. If we're integrating and we can write powers of x, then we should write powers of x. So write powers of x if you can. Just like with derivatives. If you can write powers of x, then write powers of x. So for example, if we wanted to integrate, let's say, the square root of x dx, if we can write this as powers of x, then we should, because then it'll tell us what rule to use. So I should rewrite the square root of x as an x to the 1/2 power. And then we can apply the rule that I just hid from everybody. Add 1 to the exponents and divide by the new exponent. Maybe it'll all fit. There we go. Now we can apply our rule, where we add 1 to the exponents and divide by the new exponent. And then put plus c. But we shouldn't write 1/3/2. That looks terrible. So we'll just write 2/3 x to the 3/2 plus c. Any questions? It bugs me that back in the day we chose plus c instead of plus k, the mortal constant, and we just went with the regular c constant because the plus and the c, it just becomes too sibilant. So I was like, and it's harder to say fast. And in America, we got to say things super fast. So I end up saying plusy, which is plus c, plus c, plus c, and it's terrible. It's like saying 1/6, 1/6. I don't like it because you have to take your time to enunciate those things. It's also like listing the product rule, the quotient rule, and the chain rule. Product rule is really annoying to say. I don't know why. I'm not a linguist. I'm just a mathematician trying to math his way through the world. So, in general, if we can, just like with derivatives, if we can write powers of x, then we should write powers of x, if it makes sense to do so. For example, if I've got the integral of, let's say, x squared plus 2x plus 3 divided by x dx, it makes sense to split this up and write powers of x and say this is x squared over x plus 2x over x plus 3 over x dx. Just use the distributive property and distribute the 1/x to all the 3 terms on top, because now we have 3 separate terms. So now I'm going to rewrite the 3 separate terms. We have the integral of x squared over x, which is just x, and then plus 2 plus 3 over x dx. And now we can integrate. The integral of x, we can add one of the exponents and divide by the new exponents. The integral of 2x, or 2 is just 2x. And the integral of 3 over x, this one's tricky because I didn't write this one down. Anyone know this one? What function has a derivative of 3 over x? Whatever it is, we're going to multiply it by 3. 3 natural log of x. Don't forget the plus c, and then we box up our answers. Any questions? How's everybody, okay? All right, so that's our next big thing. We're going to start learning this process here in Calc 1, and then we're going to spend an inordinate amount of time in Calc 2 learning how to find antiderivatives of things. And it's going to be extra fun, and you know that it's extra fun because at one point y'all are going to be saying, man, when am I ever going to have to do this? That's how we know it's working. It's like, oh man, this is producing suffering on a scale that I want to avoid. It's like, now we have discovered where the work has started. All right, let's pause the video here because that's going to be it for today. And I will see y'all on tomorrow.